Welcome to this lecture on pharmaceutical measurement, primarily focusing on weights and how to precisely weigh a specific amount of active ingredient. And I emphasize that accuracy because in this chapter we're going to look at the equipment we are using to weigh our drugs and look at their limitations, and that's where the idea of sensitivity requirement and least weighable quantity come in, because there are times where we might need to obtain a very small amount of drug, an amount smaller than what our scale can accurately measure directly. So in that case, how do you handle that situation? That's where we'll be learning about how to use the aliquot method of weighing and measuring. So with that as an intro, let's get started. What I really like about this chapter is it is uniquely pharmacy, meaning pharmacists have historically had the responsibility and the requirement to learn how to accurately weigh and measure very potent drugs and chemicals and combine them in a way to produce a dosage form a patient can use. This is the idea of pharmaceutical drug compounding, and you will have entire courses in pharmacy school about how to physically compound. As a part of that compounding process, you will be using scales or digital balances, as shown here on this slide, to weigh and measure your active and inactive ingredients. And clearly, the accuracy of those weights will determine the efficacy or the potential toxicity of the final product. So it is crucial that you do this. Now, like I said, historically, pharmacists have done this for many, many years. The equipment we use has changed over that time. So on the lower left, you can see an older torsion balance, which has two pans that I'll show you a little bit more in a minute that kind of go between left and right to show you whether or not the pans are balanced and have equal weights. Those worked, but they were sensitive and they took a lot more training to use correctly. What they've been replaced with clearly are the more modern digital balances shown here on the right. Regardless, both types of scales and balances have the same limitation, meaning there is a least amount of weight that they can accurately sense, and the pharmacist needs to know that so that you can determine, given the amount of error in weighings that you are allowing yourself, what's the least amount that you can weigh. And that is really the crux of what we'll discuss in this chapter. So essentially, in compounding, we need to make sure that we're using a balance that can both precisely and accurately measure the weights of our active and inactive ingredients. The USP, and you can see the definition listed here of what a prescription balance is. I guess what's important here is it's written pretty generically. That is a scale or balance adapted for weighing drugs or chemicals. Okay, it does not specify whether you have to use either a torsion balance, like I showed you with the two pans on the left and the right, or an electronic digital balance. It doesn't care so long as you're using a quality and accurate and precise balance. Because of that, most pharmacies now will use a digital balance like the one pictured here on the lower left. But going forward, even with the digital balance, all the things that we're going to talk about, maybe in terms of the torsion balance, still apply to digital balances. Because look, I blew up the display on the lower right. So it's the same picture, but blown up where I'm focusing on the display. So let's look at some things. In the display window, you can see it reads down to 0.000. So the last display digit. And if you look at below the green thing where it says the AD100, to the far right, you see where D equals. D means display. Display, the smallest amount that this scale can measure or display is 0.001 grams. So I'm just going to convert that to milligrams. So that's essentially 1 milligram. So this scale cannot display any weight less than 1 milligram. So we know that's the bottom that we can weigh. On digital balances, it can only display the smallest it can change from one weight to another weight is the last digit displayed. So it cannot sense any weight between 1 milligram and 2 milligrams. So it'll display 1 milligram, and it will display 2 milligrams. But any weight between those two is error. It cannot sense the difference between those two. Okay? Because there are some weights between increments that it can't sense, that weight is considered a possible error. All right? So I just wanted to point out on this display, do you see where it says the maximum that this scale can display or weigh accurately is 100 grams? There's a maximum. There's also a minimum. It says minimum is 0.02 grams. Okay, let me convert that to milligrams. So that means the minimum is 20 milligrams. I know what's confusing for students at this point is if the display will go as low as 1 milligram, why does it say the minimum you can weigh is 20 milligrams? Because it will display less than 20 milligrams. It'll display as low as 1 milligram. So why does it say minimum 20 milligrams? That's the crux of this lecture, to be honest with you. So I'm going to give you a quick answer while we're looking at this slide now. Do me a favor, if you got your calculators, take the least it can display, which is 1 milligram, because we said it can't display less than 1 milligram. Divide that by what, trust me on this, a typically allowable error by most state boards of pharmacy and by the USP is no more than a 5% weighing error. So if that 1 milligram can't have more than a 5% weighing error, take 1 milligram divided by 5%. So 1 milligram divided by 0.05, which is the same as 5%. 1 milligram divided by 0.05 is 20 milligrams. That's where that comes from. This display is trying to tell you to not weigh less than 20 milligrams because doing so could mean that the error in not being able to sense more than the difference between 1 and 2 milligrams, weighing less than 20 milligrams could produce more than a 5% error in your final weight. So I just thought I'd show that here. If you can do that math, you can at least maybe see where the 1 milligram, the 20 milligrams, and the 5% kind of play with each other. We're going to go and talk about that further and show you these formulas and how to make sure and do this. But we'll illustrate it with the older torsion type balance. I really think this idea of sensitivity and the limits to which a balance can accurately weigh is best illustrated using the older torsion balances. Now, these balances were the workhorses in pharmacy. If you work in a pharmacy, look under the sink, you'll probably maybe find an old one there that maybe isn't used anymore but had been around forever. They were metal, they were durable, they lasted forever. They were very sensitive for what they were, but they were difficult to use and required a lot of skill and training. Essentially, if you look on the picture on the lower left there, that torsion balance, you can kind of see it had a cover on it to keep airflow from affecting the weight measurements, but you would lift up that air cover, and it would have two pans, a pan on the left and a pan on the right. And essentially, and you can see in the picture on the lower right really well, in the middle there was a window with a red pointer and graduated markings. And again, there was a long marking in the middle that showed an absolutely even weight between the two pans. Okay. At the very bottom, there was a little metal roller knob that unlocked the pans so that when the pans were unlocked, they were free to move up and down depending on the balance of the weight between the two pans. Okay. Well, the big knob in the middle allowed you to dial weight up to 1 gram. So from anywhere from 0 to 1 gram, you could dial the weight, and that would add it to the right-hand pan. So the weight would make the right-hand pan fall down, and then you could weigh your drug powder on the left until it balanced. If you needed to weigh more than 1 gram, which you often do, then you had to add external weights, and that's why you may have seen a pharmacy weight set. It opens up and it's got little brass weights that you would use tongs to hold so that you didn't get any grease or finger stuff on there. So you would use the tongs, put the weights on usually the right-hand pan, and then you could use the physical weights along with the dialed-in weight to determine whatever total amount you wanted, and that would be on the right-hand pan. You would add then your powder to the left-hand pan. But the only way you would know whether or not the two pans were equal would be by looking at the pointer in the middle. So let's talk a little bit more about that pointer and its shifting left and right and what you could actually visually determine from that. So this slide shows a picture of the balance in the background, and what we're doing is zooming in on that window in the middle and looking at the red pointer. Now that pointer would be hovering over a scale, so you can see the black markings of the scale. There is a longer black marking in the very middle, and then alternating sizes of scales both to the left, or markings I should say, to the left and to the right of the longer midline. The lengths of the lines to the left and right were alternating in size just to help aid in visualization. The length of the lines don't mean anything. It's really their consistent width or distance from the midline, the middle marking there. So again, obviously when the pointer was marking directly over that middle longer line, then the balances there was a complete balance between the left pan and the right pan. Okay? I think that's obvious. Now, let's define the word sensitivity. This is important. We're going to define sensitivity as the smallest weight that gives a perceptible change in the indicating element. So it doesn't matter whether the change is to the left or to the right. What it means is there is enough of a weight difference that that pointer moves a perceptible amount. And here's what we're going to say. The perceptible amount, to really say it's moved from the midline, has to be at least one of those markings. So if the red point, and that's what we've shown in the right-hand picture. If you look at the lower right, we see there's enough weight on the right-hand pan that the red pointer has shifted from the midline to at least the first marking. So that weight, whatever weight it took to do that, that would be the sensitivity, because we would say that anything less than at least one marking is not enough to really be able to say it's shifted away from the midline. So again, the pointer would have to deflect at least one marking, and the weight that it took to do that would be the weight we would consider to be the sensitivity of that balance. We now know that the sensitivity or sensitivity requirement, which is abbreviated SR, so that really means the same thing. When we say sensitivity requirement, that is the sensitivity of the scale. We just said that's the weight it takes to produce a visible, measurable change that we could measure with our scale. All right, so with that, how do we actually determine it? We know what it is, but how would we know if we walk up to a scale, how could we determine what the sensitivity or sensitivity requirement of that scale is? So what we used to do with these torsion balances, we would take the smallest weight we had available externally. So we would take, and that was a 10 milligram weight. And I show you a little picture of that kind of little, it was a little metal chip that had the 10 on it, and that weighed 10 milligrams. So we would make sure our balance was completely level to begin with. We would then add that little add the 10 milligram weight to the right-hand pan. We would unlock it, close the lid so that the air wouldn't affect anything, and we would look to see how far the pointer deflected. So we know we have a fixed weight on there. The weight is fixed at 10 milligrams. We could then observe the pointer to see how far it moved over, because the formula that we would use then to determine the sensitivity or sensitivity requirement, SR, would be to take the weight that we placed on top and divide it by the number of divisions the pointer deflected. So if we, again, look at our example here, we know in the sensitivity requirement formula, on top we would put the weight we added, which was 10 milligrams. And then if you look carefully on the scale, we can see that the pointer deflected past the first division and is really right in the middle between the first and second division. So we would say it was deflected by 1.5 divisions. So 10 milligrams on top moved the pointer 1.5 divisions. So the weight per division would be 10 divided by 1.5, which is 6.7. So we would have our sensitivity requirement for that scale to be 6.7 milligrams, because it's the 6.7 milligrams that is expected to deflect the pointer at least one division from the center line. And that's what the sensitivity requirement is. It's the weight, it's the least perceptible change and the weight that can produce that. So to summarize here at this point, the electronic balance told us what the sensitivity was. It said that the sensitivity was 0.001 grams or 1 milligram on the digital balance. What we just showed you was how to determine the sensitivity requirement on an older torsion balance. By placing that weight on top and dividing it by the number of divisions, we knew its sensitivity requirement was 6.7 milligrams. Okay? That has been determining the sensitivity requirement, the smallest weight that scale or balance can sense. All right? So that's important. That's where we're at now. We got to go further, though. The point and the reason to know this, though, is because that weight will be in error. Whatever we weigh, that's the amount of weight that could be in error, because the balance can't be more precise than that amount. So it represents the error in the weighing. Okay, so the sensitivity requirement weight is the error amount we're going to assume could occur in our weighing. Well, the question is, how much error is acceptable? What percent error is allowable in our measurements? Well, before we get to see what's allowable, we have to be able to calculate what is the percent error. So keep in mind, so this is an important definition. It says the error in any given weighing will be based on this sensitivity requirement expressed as a percent of the total weight measured. So if you think about it, if our sensitivity requirement in the previous example was 6.7 milligrams, and we're only trying to weigh 10 milligrams, well, that 10 milligram weight could be off by 6.7 milligrams. That's terrible. That's more than a 50% weighing error. That would be really bad. But what if we were weighing 1 gram? 1 gram is 1,000 milligrams. So our 1,000 milligrams could be off by 6.7 milligrams. Well, 6.7 doesn't seem a lot compared to 1,000. It's much smaller. So realize, the smaller you weigh, the greater the percent error from this fixed error in your sensitivity requirement. Larger weights have that same amount of error, but it's a smaller percent of the total weight that you're measuring. Okay? So the formula is kind of important, and this is an important formula that you'll need to do some calculations with, and that is, okay, if I ask you to calculate what is the error in this weighing, what is your percent error? You would take the sensitivity requirement divided by the amount weighed, okay, times 100%. Just make sure that your units are the same. So if your sensitivity requirement is in 10 milligrams, make sure you're dividing it by the amount that you're weighing expressed in milligrams. Don't mix grams and milligrams. So you got to make sure expressed the same. When you do that, those units cancel, which is why then if you multiply by 100, you get the percent. All right? So let's practice that. But before we do, let's rearrange that formula and put in a couple of different terms, and that will be our final formula to use. Because and this is really the same formula. What I've done here is let's define the term least weighable quantity. Least weighable quantity will be a weight. Okay, it'll be the weight. It is the weight that is the least amount we can weigh given the sensitivity requirement of our balance. And in this case, instead of calculating percent error, we're going to give a percent error. What is our allowable error? Okay, how much error will I allow myself? Because if I take the sensitivity requirement and then divide it by the allowable error times 100, and that gives me the weight that that's the least I could do. Any less weight than that, then my error would be greater than my allowable error percent. So the least weighable quantity is going to be equal to the sensitivity requirement of our balance divided by the maximum amount of error we are going to allow ourselves to have in a weighing. Okay? So with that kind of as a rearranged version of it, let's use the formula in that way to answer some very common pharmacy-related questions. The first question to answer is, what is the least weighable quantity, or LWQ, when using a torsion balance with a SR, which is sensitivity requirement of 6 milligrams, and a 5% allowable error? And I will just say, some questions will use numbers other than 5%, but by law, typically that is the maximum amount you can have per weighing, is no more than a 5% error per weighing. So that is a very standard allowable error to use. Okay? So 6 milligrams for our sensitivity requirement, 5% allowable error. Well, the least weighable quantity just says to take the sensitivity requirement divided by the allowable error times 100. Okay, so in this case, we'll take 6 milligrams in the numerator divided by 5% expressed as the numeral 5, because we're going to then times by 100. So 6 divided by 5 times 100, do the math, and you get 120, and the only units remaining in the dimensional analysis is milligrams. So it's 120 milligrams. So let's just stand back. The least the scale can sense is 6 milligrams, okay, accurately. That's the most it would take to be able to move one division. But we're not wanting to weigh 6 milligrams. We don't want to weigh anything less than 120, because if my balance can be off by 6 milligrams, any weight that I weigh less than 120 milligrams would have more than a 5% error. The least I can weigh is 120. Now, what if I weigh 200? That's fine. You can weigh more than the least weighable quantity by weighing more than the least weighable quantity. The only thing that's happening is your percent error is decreasing, and that's not a bad thing. The lower the percent error, the better. But if I were to weigh anything less than 120 milligrams, that allowable error would be greater than 5%, and that's not acceptable. All right? Let's do the next example. It says, what sensitivity requirement is necessary to weigh a very small amount, only 20 milligrams on a torsion balance with no more than a 5% error? So again, how sensitive would the balance have to be to weigh 20 milligrams? All right. So in this case, if we use the formula, what do we know? We know that our least weighable quantity is 20 milligrams. We know that, and we know our allowable error is 5%. So let's use our formula and say that 20 milligrams is equal to X, which is the sensitivity requirement we're solving for, over 5% times 100. Okay, so if you do that math, 20 times 5 divided by 100 means that the sensitivity requirement would have to be 1 milligram. If your balance has a sensitivity requirement of 1 milligram, then you can weigh as low as 20 milligrams within and not have more than 5% error. Do these numbers sound familiar? This is the situation I was describing earlier with the digital balance. So that example with the digital balance, it said 20 milligrams was the least, and we knew it had a 1 milligram as its least displayable quantity, which is its sensitivity requirement, and that's where the 5% error comes in. Okay? All right, so hopefully this kind of makes sense at this point in this formula, and I will always give you this formula, but understand what least weighable quantity means, what a sensitivity requirement means. That's what we've been really spending most of this time on, and this idea of the relation between those two determines essentially a weighing error, and there's going to be a maximum allowable error that we're going to want to apply. All right, now as we transition to the term aliquot, realize what happens when you need less than that. What if you needed 0.5 milligram? Neither one of those scales can directly measure 0.5 milligram. Well, how do you do it then? You don't weigh it directly. You have to use something what's called the aliquot method to obtain the weight of drug product less than what's actually accurately measurable on your balance. This slide is an attempt to help you visualize the process involved when weighing using the aliquot method. So obviously we are doing solids at this point. So it goes back to what I just described. What happens when we need to weigh less than we can accurately measure? Okay, this picture hopefully will visualize a little bit the process and introduce some of the words and the abbreviations that we're going to use to help you figure out how to do these calculations. Okay, so starting at the far left of this image, that little bit of orange has above it the words drug needed. So that's the amount we actually want of our active ingredient. Okay. The problem is, you can see, that amount is much smaller than the pile next to it that says least weighable quantity. So that much larger amount of that same orange powder is helping you visualize my scale. I'd have to weigh that amount to be able to accurately say this is the right weight. This is a weight. But that's way more than I need. Look at this much smaller amount of drug needed. So you can't weigh it directly. Okay, so if I weigh more than I need, and that least weighable quantity has more than I need, look at it, it's much larger than that small amount. What I can do is then weigh an additional ingredient, and you see the white powder in the middle, I just call it diluent weight. That's, in this example, lactose. It's an inert powder. So I can weigh a large amount of diluent. And then what I'm going to do is I'm going to mix my least weighable quantity with my diluent. So I'm going to take my orange powder with my white powder, mix it all together, and that's what this much larger pile is on the right, where it says a much fainter orange. Do you see where the orange is fainter? Because we've mixed orange with white, it's a much lighter orange now. But it's a total mixture. So the total mixture weight is the addition of both the least weighable quantity of drug plus the diluent weight. When you add those together, you get a mixture, and you have a total mixture weight. All right? But you don't want that whole mixture. That whole mixture has all of the drug in the least weighable quantity. So what we're going to do is we're going to chop off a small amount. So you'll notice what I've done is carved off a corner of that total mixture weight. That is a fraction of the total mixture weight. We call that fraction, that small amount of the total, is called an aliquot. The aliquot is the weight of the powder that we take from our mixture, It's a small proportion of the total mixture. The aliquot weight is a smaller weight of that mixture, but that smaller weight will only contain and will exactly contain the amount of drug needed. So the aliquot weight still has to be above our least weighable quantity. We have to be able to weigh it, but it has to be a fraction of the total mixture such that that smaller amount will contain exactly the amount of drug we needed originally. So those are the steps that we're going to go through, and we'll talk about how to actually do the calculations here in a second. This picture was to help you kind of, I think, visualize some of the abbreviations and the terms that we're going to use in this calculation. This slide is another attempt to help you visualize what's happening using the aliquot method. So in this method here, on the far left, on the top, we have the little circles, the black dots. The black dots represent individual drug molecules, if you will, all right? The problem is that we only want 3 dots, okay, 3 drug molecules. But that's less than what we can accurately weigh on our scale. So in our balance, we're going to have to measure at least all of those black dots shown there. So those represent the least weighable quantity of my little black dots that certainly contain more than I want, where I only want 3. So what I'm going to do is I'm going to figure out how much diluent, and you see the diluent are triangles because the triangles aren't the drug I really want, but they're drug molecules, but they won't get in the way. So what I can do is mix my triangles with my black dots. So in the middle where it says mix, you're going to make a mixture. That mixture will contain both active drug, black dots, and triangles, inert drug, diluent, but when I mix them all together, then I have a concentration. Remember how we talked about concentration? We can determine the concentration as a ratio of the drug weight over the total mixture weight. Now, be careful, that's not diluent. We're talking about the combined weight of both drug and diluent is the total mixture. So the ratio that we use, the proportion we're going to set up, is the weight of active drug over the total mixture weight. That's a concentration. All right. Since that is a fixed concentration, what I can determine is the weight of mixture then that would just contain the amount of drug that I want. So that weight of mixture is what we call the aliquot. The aliquot is the weight of mixture that contains only the 3 drug molecules that I wanted from the very beginning, or that contains the drug weight I wanted. Okay, so the concentration does not change, but by taking out a fraction of the total mixture weight, that aliquot weight is a weight specifically determined to give me only the amount of active drug in that concentrated mixture. Okay, so remember, as we do this process, the concentration doesn't change between the total mixture and the aliquot. The aliquot's just the fraction of that weight that provides me the drug weight I wanted at the very beginning. This slide shows the 7 steps required for aliquot happiness, or essentially the aliquot method. I'm not going to read those steps to you. I'm going to talk through the example on the right-hand side. What's on the bottom are the pictures kind of to help you illustrate again and visualize that came from the textbook. Below that are the abbreviations that I use to describe that, and I'll use those abbreviations, and I try to use colors to distinguish the different parts of the steps. So as I describe what the process would be here, you can kind of look through the 7 steps and how they're written and see if it makes sense. So let me just explain the example, starting kind of on the right-hand side. In this example, shown here on this slide, we want 5 milligrams of drug. We're going to use the term DN. DN stands for drug needed. The amount of drug we need is 5 milligrams. Okay, DN equals 5 milligrams. That's what we want. In this situation, we're going to say that the least weighable quantity of our balance, so the LWQ, the least weighable quantity that I can actually measure with my balance, whether it's digital or torsion, it doesn't matter. I can't weigh less than 120 milligrams. All right? That's a problem. I want 5 milligrams. The drug I need is 5 milligrams. My least weighable quantity is 120 milligrams. So how do we deal with it? The next step is to actually determine what we call a multiplication factor. MF stands for multiplication factor. And it's easily determined by taking, this is what's important though, you put the least weighable quantity in the numerator divided by the DN, or the drug needed. So the LWQ divided by the DN, the drug needed, okay, will give you a number. this number needs to be a whole number. So if it were to turn out to be 23.2, you round up. You always round up. You never round down. If you round your multiplication factor down, then you'll get more than your allowable error. So always round it up. Okay? In this case, 120 divided by 5 is exactly 24. So we don't have to round. We don't have to round. To match the example in the textbook, they rounded to 25. Trust me on this, it gives you much nicer numbers. So instead of sticking with 24, they went ahead and rounded up to the next whole number, 25. Did not need to, chose to. Again, you can round the multiplication factor up if you want. Never round it down. Always up. So, okay, it's 24, but we're going to round it up for 25. So let's set our multiplication factor equal to 25. All right? Now, the next step is to determine the QAW, and that stands for the quantity to actually weigh. Q for quantity, A actual, W weigh. Quantity to actually weigh, and this is the quantity of our drug. Remember, we said we can't just weigh our 5 milligrams. So instead of 5 milligrams, what we're going to actually weigh is the drug needed, 5 milligrams, times that multiplication factor. So the quantity to actually weigh is the DN times the MF. So 5 milligrams times 25 means that of my drug, I am actually going to weigh 125 milligrams. Okay? I'm going to weigh 125 milligrams. Now, this is where it gets a little weird. We need to define that aliquot weight. Remember that little bit of fraction of the total that we're going to pull off at the end? That weight still has to be weighable. So the aliquot weight has to be no less than the least weighable quantity. It can be more than, like I said, you can have an aliquot weight greater than the least weighable quantity, or the least weighable quantity, but not less than the least weighable quantity. For most of the questions that we're going to work through, just go ahead. It just makes it easiest to make the aliquot weight equal to the least weighable quantity. While it can be higher, and the numbers work just fine if you choose a higher number, an easy number to remember is your least weighable quantity. You're always going to have to know that for these questions. So just say my aliquot weight will always just be my least weighable quantity. So we're going to just predetermine that to be 120 milligrams. Okay? Now, the next thing we're going to measure, or determine rather, is the total mixture weight. Remember, the total mixture weight is the combination of my active drug and some diluent, that white powder in the previous picture I showed you. The total mixture of all of that is determined by taking the aliquot weight, which is why we had to go ahead and assign that. We've assigned it the aliquot weight to 120 milligrams, times the multiplication factor. It's the same multiplication factor. It's the same value. So now, instead of doing the drug needed times the multiplication factor, the total mixture weight uses the aliquot weight of 120 milligrams in this example times the multiplication factor, which we said was 25. So 120 milligrams times 25 gives you 3,000 milligrams. That's the total weight. When I mix my drug with my diluent, I know the combined weight of that will be 3,000 milligrams. The question now, the only thing we got to know is, well, how much diluent do I need to add then? Well, I know my total mixture is 3,000, so take the total mixture weight minus, this is what's important, the quantity to actually weigh, because that's the actual amount of drug you're weighing, remember, is 125 milligrams. So take the total mixture of 3,000 milligrams minus, and I just emphasize this is where it gets confusing, the thing to subtract is the QAW, the quantity of drug you're actually weighing, which is 125. So it should make sense then the difference between those two, which is in this example 2,875 milligrams, that's the weight of diluent. You're done. So let's just make sure it makes sense. If I weigh 125 milligrams of my drug, and I mix it with 2,875 milligrams of the white diluent powder, mix it all together. Okay, that's the total mixture weight. That's a mixture. I don't want all of that. How much do I weigh out of it? The aliquot rate. Remember, aliquot means the fraction to remove of the final mixture. So I just weigh out 120 milligrams of that mixture. That 120 milligrams will only contain 5 milligrams of drug. It's magic. You should be saying, Larry, prove that. I don't believe you. I don't trust you. Prove it. Well, let's set up a proportion, okay? And this proportion, the proportion we're going to set up is let's take the quantity of the actually weigh this. So the drug we actually weighed over the total mixture weight. So we actually weighed 125 milligrams. If we set that over the total mixture weight of 3,000 milligrams, right? We have 125 milligrams in our 3,000 milligrams of mixture. Set that equal to some unknown amount of actual drug over our aliquot weight. Because remember, of that total mixture, we only weighed out 120 milligrams. So if you take essentially 125 milligrams times 120 milligrams and then divide that by 3,000, you see that X equals 5 milligrams. Remember, our 120 milligrams of aliquot was designed to only give us the drug we needed, which is 5 milligrams. All right. So hopefully, before I finish up on this slide, you can use this slide to kind of look at the visualization of these numbers down in the images. I tried to put the abbreviations below each thing that's trying to be pictured. I'll remind you that the total mixture weight has two ingredients. It has the quantity of drug we actually weighed, the QAW, plus the DW, which is the diluent weight. Well, that's why QAW plus DW equals total mixture weight. So hopefully combining an image here with these abbreviations and the process, it makes it a little more clear. Now what we need to do is practice. Let's start our first practice problem and go through, and I'll show you how to do each of the 7 steps to aliquot happiness. All right. So the problem reads, how would you weigh 10 milligrams of atropine sulfate on a torsion balance with a sensitivity requirement of 6 milligrams with an error not to exceed 5%? Okay. Well, let's identify a couple of things before we start our first step. Before we start step 1, we need to know the amount of the drug needed, how much drug do we need, and we need to know what the least weighable quantity is. So from the question, it's pretty straightforward that the drug needed is 10 milligrams of atropine. So DN equals 10 milligrams. Straight from the question, that's the amount of atropine drug that we need. What is our least weighable quantity? In the previous example, I kind of just gave you the least weighable quantity. Remember, you may need to be able to calculate it as well, because we know that the least weighable quantity is equal to the sensitivity requirement divided by the percent error times 100. So what we got from the question wasn't the least weighable quantity, but we got the sensitivity requirement of 6 milligrams and an allowable error of 5%. So we can use that. So we can say our least weighable quantity is equal to 6 milligrams divided by the 5% times 100. So if you do that math, you get 120 milligrams. So in this example, what we need is 10 milligrams, but the least we can weigh, again, is 120 milligrams. So with those 2 bits of information, we can start with step 1. Step 1 was to determine our multiplication factor. So that multiplication factor, MF, was equal to the least weighable quantity divided by the drug needed. So we can take the 120 milligrams divided by 10 milligrams. And fortunately, in this case, we get an even or a whole number. Again, it's not a fraction, so it's 12. So we do not need to round. If it was 11.6, we'd round up to 12. If it was 11.1, we'd round up to 12. If it was 12.3, we'd round up to 13. So remember, you always round to the nearest whole number. In this case, it's a whole number to begin with, and there's no reason to change it. So we will leave our multiplication factor as 12. The next step is to determine the quantity to actually weigh. So of the drug itself, the quantity we're actually going to weigh is going to be determined by taking the amount we need, which we said was 10 milligrams, and multiplying it by the multiplication factor we determined, which was 12. So 10 milligrams times 12 is 120 milligrams. And that is at or above, in this case it's at our least weighable quantity, so we have no problem weighing that. The actual amount of drug to weigh is 120 milligrams. But don't get confused with the drug needed. Remember, we only need 10 milligrams. So we are weighing 120 milligrams. That is more than we actually need. Okay, so keep in mind, though, the amount of drug we have is 120 milligrams. Next step, determine the aliquot weight. We said that this weight, this fraction that we're going to weigh out at the end of the mixture, this proportion, the small amount of the mixture that we're going to pull out, needs to be at no less than the least weighable quantity or higher than that. You can have an aliquot weight higher. And so in this example, I did choose to use an aliquot weight that's higher than our least weighable quantity just to show you that it works if you choose a number higher. We can't go lower than, and we said 120 is our least weighable quantity. So our aliquot weight needs to be 120 or higher. So let's choose a higher one just so you can see that it works. So let's set it at 150 milligrams. All right? Nothing special about that beyond the fact that it's a nice even round number that's greater than 120, not less than. All right? So set the aliquot weight at 150. We have to do that now because our next step 4 is going to determine the total mixture weight. So the mixture of both the drug and the diluent, when we combine everything, will be determined by taking this aliquot weight that we have chosen, the 150 milligrams, and multiplying it by that same multiplication factor. So 150 milligrams times 12 is 1,800 milligrams, or 1,800 milligrams. That's the weight that represents the total mixture of both drug and diluent when mixed together. Step 5 is an easy one. It is to determine the diluent weight, and we determine the amount of diluent to use by taking the total mixture weight that we just calculated, the TMW, and subtracting the amount of that that's going to be actual drug, so the quantity of drug to actually weigh. So we said our total mixture weight is 1,800 milligrams. Let's subtract out the amount of drug we're going to actually weigh. We said was 120 milligrams. Subtract those two, and you get 1,680 milligrams. That represents the weight of diluent. All right? So step 6 is to, in actuality, we would then mix those. We would take our 1,680 milligrams of diluent and mix it geometrically with our 120 milligrams of drug. So mix the quantity to actually weigh with the diluent weight. Mix that together. That creates this total mixture weight. Then, step 7, weigh out the aliquot weight. But don't get those confused. The aliquot weight we established was 150 milligrams. And you're done. 150 milligrams of the powder out of that total mixture will give us the amount of drug we need. Prove it. So let's set up our proportions of saying, okay, the quantity of drug I actually weighed was 120 milligrams. Set that over the total mixture weight, which was 1,800 milligrams of powder mix. Set that equal to some X amount of actual drug over the aliquot weight, which was the weight of the mixture we actually pulled out. Our aliquot weight in this example was 150. So 120 times 150, then divided by 1,800, means that X, or the drug amount that's provided by that aliquot weight, is 10 milligrams. And that's what we had desired to obtain. So that 150 milligrams of aliquot mixture only contains 10 milligrams of our atropine drug. Let's do a second practice problem that works very much similar to what we just completed. So in this example, though, we want to obtain 50 milligrams of chlorpheniramine maleate. The prescription balance we're using has the same 6 milligram sensitivity requirement, and again, we don't want to have more than a 5% weighing error. So how do we go about obtaining that 50 milligrams of drug? The first thing to do is to determine the actual amount of drug needed. So our DN, or drug needed, is pretty straightforward from this question, and it's the 50 milligrams of the chlorpheniramine. So our drug needed is 50 milligrams. Again, we'll need to calculate the least weighable quantity as the second step, in that we need to use the formula and say that our least weighable quantity is equal to our sensitivity requirement of 6 milligrams divided by our allowable error of 5% times 100. So that gives us 120 milligrams. All right. So those are kind of our pre-steps. So step 1 of actually determining the multiplication factor, we do that by taking the least weighable quantity divided by the drug needed. In this case, we take 120 milligrams divided by 50 milligrams, and that equals 2.4. And I know I've emphasized this enough. What we need to do is take that multiplication factor and round it up to the nearest whole number. So 2.4 would be rounded up to the number 3. So our multiplication factor in this question will be 3. Step 2 is to determine the actual amount of drug quantity to weigh. So our QAW, the quantity of drug to actually weigh, is determined by taking the amount the drug needed, which we said was the 50 milligrams, times the multiplication factor we just determined of 3. So 50 milligrams times 3 is 150 milligrams. So we will, in fact, weigh 150 milligrams of our chlorpheniramine. All right? Now, take a break. Let's choose our aliquot weight before we go any further, As I said before, this can be the least weighable quantity or a value higher. And in the previous example, we chose a value higher. But in these examples, let's just choose the least weighable quantity. That's an easy one to remember. So the aliquot weight will just set equal to our least weighable quantity of 120 milligrams. Okay, now that we know that, we can go to step 4, which is to determine the total mixture weight, that of both the drug and the diluent, the total mixture combined. Let's take our aliquot weight that we just picked, which was 120 milligrams, times the same multiplication factor of 3. So 120 times 3 means our total mixture weight will be 360 milligrams. Step 5 is to determine the diluent weight, and we do that by taking the total mixture weight we just calculated at 360 milligrams and subtracting the quantity of drug we're actually going to weigh, which we said was 150 milligrams. So 360 minus 150 means we need 210 milligrams of diluent. So step 6 is just telling us take that amount of diluent, 210 milligrams, mix it with 150 milligrams of the actual drug, mix that all together to get your 360 milligrams. And step 7 says then weigh out only the aliquot weight of that mixture. So we set the aliquot weight to 120 milligrams, so that's the weight of the mixture we'll weigh out. That's the amount that will contain the amount of drug needed. Let's prove it by setting up our proportions again. The quantity of drug we actually weighed was 150 milligrams over the total mixture weight it resided in, which was 360 milligrams. Set that equal to the amount of drug we want, or X, that we're trying to solve for, over what we weighed out of the mixture, which is 120 milligrams of mixture. So 150 times 120 divided by 360 means that the amount of drug in our aliquot weight is 50 milligrams, which is what we had targeted. Here, I'm just trying to show you what happens if you were to choose an aliquot weight greater than the least weighable quantity. So again, in our previous example we chose 120 milligrams as our aliquot weight. What would change if we chose 150 milligrams for the aliquot weight? My point to you is that what does not change is the quantity to actually weigh. The quantity to actually weigh will always be fixed at the drug you need times that multiplication factor. Again, the multiplication factor doesn't change. Drug needed, multiplication factor doesn't change. Therefore, the quantity to actually weigh does not change. Even if we choose an aliquot weight of 150 milligrams, we still need 150 milligrams of our actual drug. By choosing a larger aliquot weight, what you see happens is that the total mixture weight will increase because now we're going to take that aliquot weight times the multiplication factor. So now we have 450 instead of 360. So that's gone up, certainly. But then the diluent weight will also go up because that 450 minus that number that doesn't change, the quantity to actually weigh, so it's now 450 minus 150 gives us 300. But it still works. So look at the proportion. Now we have the quantity to weigh of 150 over 450 equal to X over 150 because our aliquot weight is now 150. So 150 times 150 divided by 450 is still 50 milligrams. What would the numbers look like if we increased it even higher to 200 milligrams? Well, if we increase the aliquot weight to 200 milligrams, again, it doesn't change the quantity of drug to actually weigh. Our aliquot weight is 200. Our total mixture weight increases because we take 200 times 3, gives us 600. Now our diluent weight increases because 600 minus 150 is 450. But the proportion of 150 over 600 is now equal to X over 200. So 150 times 200, but divided by 600, still gives you 50 milligrams. So the take-home message here is you need to set the aliquot weight at no less than the least weighable quantity, but choosing weights higher than that gives you the same ultimate results, even though it does produce more waste in one sense in that you're having to weigh more diluent and weigh more out for your aliquot weight, but it still works. One more practice problem that works very similarly, but let's mix up the numbers here a little bit. And I'll also give you some multiple choice answers just so you can see if you were to accidentally fall into one of those mistakes and get a different number. So the problem reads, we want 20 milligrams of a substance. So some drug, we need 20 milligrams of it. We're going to use a torsion balance with a sensitivity requirement now of 6.5 milligrams to obtain this drug, but we don't want an error more than 2%. Okay, so 6.5 milligram sensitivity requirement, 2%. Now, this part that I show you here that's italicized is how I will include on my exam. So any aliquot question I typically give you on exam will end with this: using the smallest possible whole number multiples and aliquot. That's saying I need you to use the smallest whole number multiple of your multiplication value. So round it up, but round it up to the nearest whole number. Don't go higher than that. And also at the smallest possible value for the aliquot. Hopefully that should tell you that means it has to be the least weighable quantity. It can't be less than the least weighable quantity. And I just showed you how you can choose aliquots greater than the least weighable quantity. But for me to grade these things on the exams, I need you to all answer this question the same way. So when I say the smallest possible value for an aliquot, that means you have to use the least weighable quantity value for the aliquot. So having said all of that, see if you can solve this question and get the right answer. Here is my solution where I show my work over here on the right-hand side. And hopefully, since this is the third solid example we've done like this, that I'll go through this a little more quickly. In the question here, the first step, we know the drug needed is 20 milligrams. The little bit of a trick here is I need to calculate my own least weighable quantity, and the numbers are a little bit different. So in this case, I was told the sensitivity requirement was 6.5 milligrams divided by the acceptable error now, that is 2% times 100, means that my least weighable quantity is now actually 325 milligrams. Okay, so let's determine the multiplication factor by taking the 325 milligram least weighable quantity divided by the drug needed, which gives me kind of an ugly number of 16.25. I don't care. I'm going to round it anyways, and I'm going to round it up. So I'm going to round 16.25 up to the nearest whole number, which was 17. Now, this is where I'd stop for a second and say my question here. You may think, well, let's just round that up to 20. And frankly, you could answer this question by rounding up to 20, but rounding up to 20 is not using the smallest possible value for the multiple. So remember, in this case, when I say that in my question, you need to round up to the nearest whole number of 17 in this example and stick with it. So 17 is my multiplication factor. Next step, quantity of drug actually to weigh is to take the drug needed of 20 milligrams times my 17 multiplication factor and get 340 milligrams. That's the amount of drug I'm actually going to weigh. What's my aliquot weight going to be? Remember, because of the question saying to use the smallest possible value for the aliquot means I can't use anything less than 325 milligrams. So that's what I'll set for my aliquot weight. Now, my total mixture weight will be my aliquot weight times the multiplication factor. So 325 times 17 gives me 5,525 milligrams of total mixture. To determine the diluent weight, let's take the total mixture and subtract out the drug quantity to actually weigh. So that was the 340 milligrams. So 5525 minus 340 gives me 5,185 milligrams. And again, that represents the diluent weight. So at this point, I take my 5,000, and that's essentially the answer to this question, because the question basically was asking you what diluent weight in milligrams is required. I'm sorry I didn't really specify that, but that's what the question wants, is the diluent weight. So the right answer for this question would be 5,185 milligrams. Let's prove that that works by going back and setting up the drug I'm actually going to weigh. The quantity to weigh is 340 milligrams over my total mixture weight of 5,525. Set that equal to some X amount of drug over my aliquot weight, which is now 325. So 340 times 325 divided by 5,525 gives you 20 milligrams, which was the amount of drug that we desired. And lastly, I won't point through that, but below the multiple choice questions, you can see where some of the wrong answers came from, that sometimes these are errors that students have done in the past. I hope by now you have a solid grasp of how to do the aliquot method using solid, because every example to this point we had a solid drug mixed with a solid diluent, mix them together and weigh out a solid fraction or aliquot. Well, what happens if the drug is a liquid? Because, depending on the apparatus you're using to volumetrically measure your drug, there may be limits to how small a liquid volume you can measure. Imagine a 10 milliliter cylinder. You're not going to be able to measure half a milliliter of liquid using that sort of apparatus. So what happens when your volumetric measuring devices have a least measurable volume and yet the drug volume that you want is less than that. See, now I'm saying volume instead of weight. So in this case, we still do the same sort of aliquot. Luckily, the system works almost exactly the same, but keep in mind what we're talking about now is our drug is pictured here in these same little 3 drug circles. Those are from a liquid. It's in a liquid form. So our active drug is a liquid. So we're going to measure a certain amount of that and mix it with a diluent again. But this diluent in this case usually is water. Not always, but let's just picture water. So our liquid drug mixed with a certain amount of water gives us a concentration. Now again, we had to measure more of our liquid drug than we wanted, so there's more drug in this mixture than we want. So what we need to do is extract out a fraction of that volume that contains the amount of drug that we want. So again, it works exactly the same as what we described, but the issues of least weighable quantity are now replaced with issues of least measurable volumes or least measurable quantities. So let's talk about the apparatuses used to measure liquids used in pharmaceutical compounding. So the differences I want to point out between solid aliquots and liquid aliquots has to do with, again, keep in mind we're now going to be talking about least measurable quantities. Those least measurable quantities need to be in whole numbers for the volume, for milliliters. So we don't want to try to set a least measurable quantity of 2.8 milliliters. We'd want to round that to a whole number of 3. Likewise, your multiplication factors, just like we talked about before, also still need to be rounded up to whole numbers. So you don't use 2.5, you'd round it up again, rounding it up to 3. So round your least measurable quantities and round your multiplication factors. Now, there is no sensitivity requirement for graduated cylinders, if you will. They may give you a plus or minus error. So if you look in the graduated cylinder on the left, the glass one, if you look carefully there, you can see where it says plus or minus 0.1 milliliters. So they might, again, give you an estimate of how sensitive or how accurate the markings on the side will be. Other ones, like the cylinder on the far right, don't say anything about that. So typically, there's a general rule that says, well, then the safest thing to do is to make sure you never use less than the 20% of the value. So don't measure a volume less than 20% of the cylinder. So for a 10 milliliter cylinder times 0.2 or 20%, that would be 2 mils. Generally, shouldn't use less than 2 mils, which is why on the cylinder on the right, you can see that it doesn't even give you a 1 milliliter marking. It basically starts at the 2 milliliter mark. All right. However, this is not an absolute rule because there are some more precise, higher grade cylinders whose accuracy, like the glass one on the left, would allow you to measure as low as 1 milliliter potentially. So the take-home rule will be, for volume, I will always provide you, for the apparatus I'm giving you in the question, whatever that is, I will tell you the least measurable quantity. You do not have to calculate it. So let me just emphasize. Least measurable quantity or volume of a measuring apparatus will be provided you to in the question, because that 20% rule is a general rule, not an absolute. So I will always provide it to you. You don't have to calculate it like you do have to be able to calculate the least weighable quantities. Let's complete our first practice problem on using liquid aliquots. So in this problem, it states that a formula calls for 0.5 milliliters of orange oil. Now we're going to be using alcohol as a diluent and a 10 milliliter graduated cylinder that's calibrated in 1 milliliter units ranging from a low of 2 to a top value of 10 milliliters. And it's the cylinder pictured here in the lower right. Okay, so that's the cylinder. How are we going to obtain the desired quantity of orange oil, assuming that using that cylinder, the least measurable quantity we should use is 2 milliliters? Well, we start this problem like every other aliquot problem with determining the drug needed. And so from the question, we know what we need is 0.5 milliliters of the orange oil. That's the drug that we need. We can also see using that 10 milliliter cylinder that the least measurable quantity for that is 2 milliliters. That was given to us in the question. So let's determine our multiplication factor by taking the least multiple quantity of 2 milliliters divided by the drug needed, or 0.5 milliliters. And we see that our multiplication factor is 4 exactly, so we don't need any rounding for that. Okay? Well, what is the actual quantity we're going to measure of our liquid orange oil? Well, we would take the drug needed amount, 0.5 milliliters, times the multiplication factor and see that we will in fact be measuring 2 milliliters of the orange oil. Let's stop and set our aliquot volume. We want to set our aliquot volume this equal to our least measurable quantity, so we're going to say that's 2 milliliters. Therefore, the total mixture volume will need to be that amount, the aliquot volume of 2 milliliters, times the same multiplication factor of 4. So 2 times 4 is 8 milliliters. Our total mixture, when we have both the orange oil and the alcohol mixed together, the total mixture will be 8 milliliters in volume. So the question is, how much diluent volume, how much alcohol do we need? Well, let's take that total mixture volume of 8 milliliters and subtract the quantity to actually measure of 2 milliliters. So 8 minus 2 is 6 milliliters. That's the diluent volume. That's the volume of the alcohol. So what we're going to mix is 2 milliliters of orange oil with 6 milliliters of the alcohol. When we mix that all together, remember, we don't want all all 8 milliliters, I should say. We only want the part that gives us the 0.5 mils, which would be our aliquot volume. So after we mix the 6 and the 2 and we have a total of 8, we measure out 2 milliliters from that 8 and use that 2 milliliters as our source of active ingredient. Because if we look at our final check down here, if we have the 2 milliliters of the oil that we actually measure over the 8 milliliters of the total mixture volume, set that equal to X amount over the 2 milliliter volume of our aliquot volume. 2 times 2 is 4, divided by 8 would give us that there is 0.5 mils of orange oil in our aliquot volume. And that would be the right answer and procedure for this question. Now, just for the fun of it, let's do that same exact question where we're trying to measure 0.5 milliliters of orange oil, and we're going to use alcohol as a diluent. But now, as you can see in the picture on the lower right, we're going to use a 50 milliliter graduated cylinder instead of a 10 milliliter. So what does this mean? It means the cylinder, which is marked in 1 milliliter increments, goes from a minimum measurable volume of 5 milliliters to a maximum of 50. So this question is basically answering the same question, but now our least measurable quantity is 5 milliliters and our maximum is 50 milliliters. So how would that change the question that we just did? So we'll start off with the same amount of drug needed. So we still need 0.5 milliliters of the orange oil. And the question told us with the 50 milliliter cylinder, the least measurable quantity now is 5 milliliters. So step 1, to calculate the multiplication factor, would take the least measurable quantity of 5 milliliters divided by the drug needed, which is 0.5 milliliters, and we see that the multiplication factor is 10. Exactly, so no rounding is needed. So next we'll determine the quantity of our drug to actually measure by taking the drug needed of 0.5 milliliters times 10, and we see that equals 5 milliliters. Next, we'll decide on our aliquot volume. We'll choose the least measurable volume for our aliquot volume as well. So we'll choose 5 milliliters for that. That makes the total measurable volume equal to the aliquot volume of 5 milliliters times the multiplication factor of 10, which equals 50 milliliters. Therefore, our diluent volume will be to take that total mixture volume of 50 milliliters minus the quantity to actually measure, which was 5 milliliters of the orange oil. The difference is 45 milliliters, which we see we can measure since that is less than the maximum of 50. So we would mix 45 milliliters of alcohol with 5 milliliters of orange oil and extract back out of that mixture the aliquot volume of 5 milliliters. So let's prove that that 5 milliliters does contain our 0.5 mils of orange oil, because we can set up our ratio of our quantity to actually measure of 5 mils over the total mixture volume of 50 mils, set that equal to some unknown amount of the drug over the 5 mils of the aliquot volume. So 5 times 5 divided by 50 equals 0.5 milliliters, and that shows that we do get our desired amount of drug in the end. All right, it's here, the third and thankfully final aliquot variation. So believe it or not, you can do these same sorts of calculations when you have a drug that goes back to a solid. So in this example, if you look on the black dots, this is solids. Just like when we had our drug mixed with lactose and we weighed out a certain amount of the mixture powder. In this case, what's different here is we still have a drug as a powder, or a solid, if you will, those black dots. But now what we're going to do is disperse those and dissolve them, most likely in a liquid solvent. So let's dissolve it in water. So we're going to weigh more than we need, because we need only 3 dots, but our least weighable quantity are all of those dots, so we're going to weigh extra. And what we're going to do is mix them then with a liquid diluent. So the solid will either dissolve, solubilize, or disperse within that liquid, resulting in a concentration. So there's going to be so many milligrams per milliliter, for example, of the drug in this mixture. Okay, and so even if it dissolves, just because you can't see it doesn't mean it's not floating around there. So as long as we assume that it is evenly dissolved or dispersed, and so the concentration is uniform through that entire liquid mixture, what we can do is extract the volume now of liquid mixture that provides only the 3 dots that we want. So it really works kind of exactly the same. We're still going to weigh more than we need because of the least weighable quantity. We're going to disperse or dissolve that drug in a liquid solvent, and then take an aliquot, a fraction of that liquid volume that provides just the amount of drug that we need. All right, well, let's try a practice problem by first reading and interpreting this prescription, and then we'll look at the details under the problem section. It's a pretty straightforward prescription. Basically, what's been prescribed is a drug or a chemical known as tartar emetic. So think of this as a solid powder. And what we need is a weight of that powder of 0.015 grams. But what we're going to want to do is dissolve or disperse that solid in a liquid. In this case, we chose a liquid that might cover up some of the nasty taste from the powder, so we chose to use cherry syrup. So, cherry syrup, the QSAD is a Latin abbreviation that means up to a total of. So what we're going to do is we're going to put in our powder and then start adding our liquid until we get a total volume of 120 milliliters. So my final volume, when both the powder and the cherry syrup are combined, it will be to a total of, which is QSAD, to a total of 120 milliliters. So hopefully you're kind of seeing a concentration there. We have a weight of a drug into a total final volume there. So we can kind of get that from the prescription. Now, additional information under the problem says to make this, we are going to be using a balance with a sensitivity requirement of 4 milligrams and acceptable weighing error of 5%. Okay? So the question says, how would you obtain the correct quantity of the tartar emetic to fill the prescription using what you have available is a beaker. So we're going to mix the powder and the cherry syrup in this 50 milliliter beaker. But to measure the actual volume of the liquid, we'll need to use either a 10, 25, or 50 milliliter cylinder. So with that as a setup, how would we approach to prepare this prescription? Let's start this problem the same way we've dealt with all the aliquot problems, is to first identify the weight of the drug needed. So this question was made a little more difficult by expressing that in grams. So we need 0.015 grams. And that's fine, but that's an awkward number to use. So I think it will be easier if we go ahead and convert that value to milligrams. So to convert grams to milligrams, we're going to multiply by the fact that there's 1,000 milligrams per gram, so that grams cancel. And when we multiply by that, we see that the amount of drug we need is actually then the same as 15 milligrams. So we need 15 milligrams. Next question, well, what's the least we can weigh? Well, we're going to have to calculate our least weighable quantity. We're good at this by now. So we'll take our sensitivity requirement of 4 milligrams divided by the allowable error, which we said was 5%, times 100. So we do that math, and we see that our least weighable quantity is 80 milligrams. Darn. That means we can't just weigh the drug that we need. We need 15, but we can't weigh less than 80. So we are going to have to do an aliquot here. So let's do the first step in the aliquot, which is to calculate the multiplication factor. So we'll take the least weighable quantity of 80 milligrams divided by the drug needed, which is 15 milligrams, and we see that 80 divided by 15 is 5.3. That's not a round number. We're good with that. Stay calm. We're going to round, but remember we round up. So our multiplication factor will be set to 6. Now that we know our multiplication factor, we can determine the actual amount of this tartaremetic drug powder to weigh. We're going to take the drug needed amount, 15 milligrams, times this multiplication factor, so 15 times 6 is 90. So we are now know that we will be weighing 90 milligrams of the drug powder. At this point, I need to clarify some additional information. We know how much drug we're going to weigh, which is 90 milligrams. At this point, we're going to assume that the drug is freely soluble, so that the tartar emetic will dissolve in basically any reasonable volume of the cherry syrup. It's very water soluble, so it will dissolve. So we're not constrained by having to use a minimal amount of volume just to dissolve the drug. So the drug will dissolve in pretty much any volume. So that frees up our ability to make some choices. So let's make a choice. We have some options. In this example, I chose to use the 10 milliliter cylinder to measure out my aliquot, because we did an example like that before. So if you remember, we said for a 10 milliliter cylinder, generally the least measurable volume is about 2 milliliters. So let's use the 2 milliliters as our aliquot volume. Okay, so our aliquot volume will be 2 milliliters using the 10 milliliter cylinder. Now, what we're going to make, though, the total mixture volume is going to be that aliquot volume of 2 mils times our multiplication factor, which was 6. So 2 times 6 is 12 milliliters. And so what does that mean? What that means is, and you'll notice here there isn't really a diluent volume, because here's what we're going to do. We're going to weigh 90 milligrams of that drug powder. We are then going to dissolve it in the total mixture volume. So again, 90 milligrams, and then we add to that 90 milligrams, we QS with the cherry syrup up to 12 milliliters. And we mix it up and we let the drug dissolve. So we have 12 milliliters essentially that contains 90 milligrams. And that's shown here in this proof at the bottom, where we show that the quantity to actually measure is 90 milligrams. We set that over the 12 milliliters that we have dissolved it in. Now, remember here, we don't want that 12 mils. That 12 mils has 90 milligrams. So what we want is the aliquot volume. We'll measure out of that total mixture volume the aliquot volume, which we said was 2 milliliters. So let's prove that that works. So if we put the 90 milligrams over the 12 mils, set that equal to X over our aliquot volume of 2 milliliters, we solve for X, we see that 2 milliliters contains the 15 milligrams of drug. So just to visualize this, you take your 90 milligrams, you dissolve it in 12 milliliters of cherry syrup, you withdraw 2 milliliters, your aliquot volume, that remaining 10 milliliters is thrown away, is discarded. You don't want that drug. You only want the drug that's in the 2 milliliter aliquot that you took back. So in this case, what would the diluent volume be? Well, and again, a diluent is cherry syrup. Well, we have 2 milliliters. We would need to add an additional 118 milliliters of cherry syrup to our 2 milliliter aliquot. That would give us a total volume of 120 milliliters. And we can see that 2 milliliters of aliquot provided 15 milligrams. So that's how we could correctly compound this prescription, even though we can't weigh less than 80 milligrams. Here I want to just show you how the math would work out if we made a different decision relating to the volume to dissolve our drug in. So in this example, which is the same question, we are still at the situation. So we still have a quantity to actually weigh of 90 milligrams. Remember, based off all that math, that's still the same. But that 90 milligrams, we said it was freely soluble. So what if we want to use the 25 milliliter cylinder? Well, if we use that one, then we can measure more than 2 mils. So let's just choose, and this is a choice because, again, the drug is freely soluble. So instead of 2 mils, let's choose 8 mils. I can measure 8 mils in a 25 mil cylinder. So if I choose to make my aliquot volume larger at 8 milliliters, okay, so I make that choice, then my total mixture volume will be the aliquot volume of 8 milliliters times 6. So you can see that's 48 milliliters. All this means is that I'm going to take my 90 milligrams of drug and now dissolve it in 48 milliliters. Okay, so I dissolve all of that, and you can see the proof at the bottom. If I put 90 milligrams over 48 milliliters, set that equal to some unknown amount X of drug over the aliquot volume, which we said is 8 mils I'm going to measure out. Well, solve for X, and X is equal to 15 milligrams, so it works out the same. But so now to compound this, my 90 milligrams is dissolved in 48 milliliters, right? Mix that all up. But then remember, I don't want the 48 milliliters. I'm going to measure out only 8 milliliters. Discard the remaining. So I throw away 40 mils and I'm left with only 8 milliliters of that total mixture volume. From that 8 milliliters, has enough drug, but I need to bring it up to 120 milliliters. So now I would add 112 milliliters of cherry syrup to my 8 milliliters of the aliquot. I'd still end up with 15 milligrams of drug in 120 milliliters. So truly, by weighing more, you can use an aliquot volume pretty flexibly to be able to calculate and prepare this compound. Phew, we are done with aliquots. So just to summarize, we have talked about using the aliquot method when we need to weigh less drug and use it in a solid. So when we have a solid drug with a solid diluent. We've done aliquots when we have a liquid drug that we mix with a liquid diluent. And we just now finished up a solid drug mixed with a liquid diluent. So any one of those, they all follow a very similar procedure for how you could go about using the aliquot to calculate that. So let's move on to the next topic, which is calculating a percent error. And this is an important idea because when we compound or we make measurements and say the target or the expected amount we want in our prescription is 3.6 grams. Well, what if we weigh 3.589 grams? Is that close enough? Do we have to get exactly to 3.6 grams? How close do we have to be? Usually, most compounding standards in general in pharmacy are that you have to be within 5%. Well, if you have to be within 5%, you need to be able to calculate what your percent error is in any weighing or measuring. Okay, so this is the formula to calculate the percent error. You're going to take the actual value you got. So this is what you weighed or what you measured, whatever it was, the actual value you obtained. Subtract the expected or the desired, what you had wanted or what you expected to get. So this is what would be in the formula. So the expected value is subtracted from the actual value. And then you divide that, and this is what's important to remember, by the expected. You're trying to calculate your percent error from what you had desired or expected. So take the actual minus the expected, divided by the expected, times 100 to convert it into a percent. So that's the formula we'll use for calculating a percent error. Let's practice that with a problem here. So this problem says that a 10 milliliter graduate cylinder weighs 42.745 grams. That's the actual weight of the glass cylinder. Now, when 5 milliliters of distilled water are measured in it, then we put that on a scale and measure the combined weight to be 47.675 grams. Okay. Now what we know is by definition 5 milliliters of water should weigh 5 grams because the density of water is 1 gram per milliliter. So 5 milliliters should theoretically or be expected to weigh 5 grams. So in this example, go ahead and calculate the weight of the measured volume of water and express any deviation from 5 grams as a percent error. So that's what we're trying to solve in this question. Well, let's go ahead and solve this. Well, we'll answer the first question, which wants to know the actual weight of the water that we measured. So if we take the combined weight of both the cylinder and the water of 47.675 and subtract the weight of just the empty cylinder, which we said was 42.745 grams, then the difference between those two and our actual recording of the weight of our water was 4.93 grams. So that's our actual, 4.93 grams. What we expected was that 5 milliliters would have been expected to weigh 5 grams. So we have an actual value, 4.93, and an expected value of 5. So let's go ahead and calculate that percent error. Remember the formula said to use the actual first. So we'll take the 4.93 actual, subtract 5 grams, and then divide that result by 5, which is our expected value, times 100. And what we get is a negative value of 1.4%. And that's why I like this version of the formula, because if your value is negative, it means you were less than what was expected. So a negative value in this formula simply means negative is less than the expected amount. If your value is positive, then you weighed more than the expected amount by that percent. So in this case, we were below what was expected by 1.4%. Our next problem says that a pharmacist used 28.35 grams of zinc oxide instead of the 31.1 grams called for in the formula. Therefore, they're not exactly the same number. Is that acceptable? Well, let's determine it by calculating the percent error based on what we desired. And I give you some multiple choice answers there to see if you can determine what the right answer is. So to solve this problem, we need to identify that the 28.35 that the pharmacist actually weighed was our actual, and what we had desired or expected from the formula was the 31.1 grams. So let's use the formula. We'll start with the actual of 28.35 grams. Let's subtract 31.1 grams from that, which is the expected. Divide it by 31.1 grams, the expected value, times 100, and we see that result again comes out negative 8.8%. So once again, the negative simply means that our amount was less than what we had expected by 8.8%. And by most examples in pharmacy, that percent error would be too much or not be an acceptable or an allowable error being greater than 5%. The last section in this chapter to discuss is this idea of estimation. An estimation simply helps you confirm that your real answer, seems reasonable. It can help you prevent errors by identifying mistakes in your calculations. When we talked about the 4 C's of pharmacy calculations, we talked about compute. Compute is important, that you're able to add, subtract, multiply, and divide your numbers accurately. But sometimes mistakes happen. And the last C was this critically evaluate. And that is important, and that's essentially what we're trying to do with this estimation. It helps us determine whether our answers are logical and reasonable. Does that seem plausible that a patient would have that dose or would consume that volume? So this critically evaluate certainly is difficult and increases with experience. The more problems you deal with, the more you kind of see typical values for body surface areas and doses, then it makes sense. One thing you can do until you get to that point is to try to estimate your answers. And I'll give you an example of that on the next slide. So here's a simple math calculation where you need to take 317.4 and multiply that by 21.3 and divide that result by 62.5. So can you quickly now tell me what that answer is? Probably not. If you're like me, you would want to get a calculator out and carefully put those numbers in. So go ahead and do that now. If you can't just tell me exactly right what the number is, go ahead and get your calculator and determine what the final answer is for that formula. Well, hopefully you were able to exactly calculate the answer to be 108.2. And that is the right answer for this. Or is it? Does that seem a reasonable answer for that? Well, could we estimate what the answer is by rounding the numbers to something we could more simply multiply, even maybe in our head, mental math, to be able to determine that? So let's round. Instead of 317.4, let's estimate that to be at roughly 300. And then the 21.3, that's 20. And divided by 62.5, let's round that to 60. So really what we are estimating here, to get a close number, we could just take 300 times 20, which is 6,000, and then we can divide that quickly enough with the 60 to get 100. So without even having to use a calculator, I could estimate this value to be 100. Then I can do it for real, and I can see my actual value of 108.2 seems reasonable. But keep in mind, an estimation is not the correct answer. So the correct answer to this question is 108.2. But we were able to kind of quickly estimate that our value that we obtained through all of our math is reasonable and that our final answer is probably correct. Let me ask you this. If on one of your questions you've calculated that the oral dose of a single dose of a tablet should be 10 grams, does that seem reasonable? Well, wait a minute. Let's see. 10 grams. Most drugs are dosed in milligrams. So if I take 10 grams times 1,000 milligrams per gram to convert it to milligrams, that 10-gram answer really is saying each dose would be 10,000 milligrams. That seems really high. I've never seen a tablet that's large. For example, on this slide, I show you a couple of pictures of some of the largest size tablets I could think of, including a 500 milligram Tylenol or acetaminophen, 1,000 milligram levetiracetam, and a 1,000 milligram metformin tablet. nowhere near 10,000 milligrams. So with a little bit of experience, that strength of a tablet is well outside of my experience, so I would question that as not being a reasonable answer. Well, let me ask you one final question. Thankfully, it's the final question. What if a student calculates a final volume of their answer for a patient to consume 20 liters of medicine for her prescription? Does that seem reasonable? No, it's not reasonable. 20 liters is as much as a 5-gallon bottle or 10 2-liter bottles of soda pop. I'd rather go with the soda pop myself, but either way, 20 liters is a huge volume, and that wouldn't be a reasonable. I would absolutely be concerned about how accurate that answer is. And I make fun and use some dramatic examples here, and they're not as easy when you're working on them, but it's always important that after you finish your calculation that you look at that answer and pull yourself out of your detailed mathematical computation and think, okay, does this number seem like a reasonable number? Is that something that can be weighed or measured, or is that an amount a patient could be expected to consume? Try to think about what your answer really represents in the real world and decide if it seems reasonable. And now this definitely takes time to develop this skill, but it is something that we are really wanting you to move forward to be able to get to this ability.